This is the second video for Lecture 8. This video is going to focus on accessing census data in R. So the previous video introduced American Fact Finder, which is the web interface for accessing most of the Census Bureau's products. Some of the Census Bureau's products can be accessed directly from R, however, and this is ultimately a huge time saver for doing demographic research. The three things I want to talk about in this video are setting up tidycensus, which is the R package we're going to use to access census data. It's not the only R package that's available for doing this, but it is the easiest to work with. I want to talk about downloading census data with tidycensus. And then finally, I want to talk about downloading American Community Survey data with tidycensus. Both of those census products were introduced in the previous video. So first, I want to talk about tidycensus. It does require a setup process, and that setup process is due to the fact that it needs an API key. That API key can be obtained from the Census Bureau. You enter your information, you should get an email pretty quickly afterwards with a very long string of letters and numbers. API stands for Application Programming Interface. It's essentially a predictable set of information that is returned when a particular website is called. And the way tidycensus works is it makes calls to the Census Bureau servers on your behalf, and information is only returned when a census API key is present. So before you go any further, make sure you've got that API key handy. Once we have an API key, we want to add it to our R environment file, which is a file that you don't normally access, but you can store information about yourself in that packages can call later on. We'll do this with tidycensus. There is a function specifically for this purpose called census API key. It takes two arguments. One is the key itself that needs to be wrapped in double quotes. This is a very long string of letters and numbers, and so you'll want to copy and paste this. Don't try to type it in yourself. And then secondly, we're going to set install equals true, and this means that we only have to enter it once per computer that we're using. So here's what it looks like in practice. We enter that long key in. This is a shortened version of it here. It's a fake API key. And then we'll use that install equals true argument. Once we execute this function, we need to restart our R session. We can do this by completely closing and reopening RStudio, or going to the session menu and choosing either new session or restart session. Any of those three options will work, and I'll demo one of them in just a second in this video. So here we have a new R session. I'm going to start by opening up the tidycensus package. And then I want to call that census API key function. We're going to enter our key. I've entered mine here and blurred it out. You'll enter yours. And then we'll make sure we use that install equals true argument. We hit enter. We'll be told that the key has been stored and that we need to restart R. And so I'll demo what it looks like going to the session menu and clicking restart R. Now that we have tidycensus set up, I'd like to download some census data. And so we'll start from downloading data from the decennial census. This is the census that's conducted every 10 years in the United States by order of the Constitution. And there are thousands of variables that we could potentially download from that census. The easiest way to find variables from within R is to use tidycensus's load variables function. The load variables function takes three arguments. We give it a year if we're looking for censuses that would either be 2010, 2000, or 1990. If you need older census data, you'll have to use a different tool, not tidycensus. And then we enter a product, and the main product we're usually interested in is called SF1. This is the main US census, particularly for 2010. Finally, we'll set cache equals true. If you have to re-execute your notebook, for example, this will make that second execution go quite a bit faster. So here's what it looks like. I always recommend loading the variables into an object This way we can preview those variables at will. And so I've loaded them into an object called Census here. There's a notebook available on GitHub for this session. And we'll start by loading the dependencies. And this notebook requires two, tidycensus, the primary package we're working with, and we'll use dplyr just a little bit at one point. So we'll load both of those. We've already installed the API keys. So we'll go right to loading variables from the 2010 census. We'll get the data from the SF1 product and make sure we've cached the output. It will take a few seconds to download and load into your global environment. When it's done downloading, we can go ahead and open up that object. And we get a table that we can scroll through to look for different variables. But there's so many, almost 9,000, that it's much easier to search. And there is a search field. So we can search either by variable name. I found the total population variable here. This is helpful if you already know what you're looking for. Or you can search by concept, total population. This will at least help you limit the number of rows that are returned to scroll through. Once we know what variable we want, we can use the getDecennial function to download it at any level of geography it's available for. So typically, data can be downloaded either at the state level, the county level, the tract level, or the block group level. This is going to be specified in the geography parameter. We also want to note what year we're downloading the data for. One note of caution here, tract boundaries change for each census. So the 2010 tract boundaries are not the same as the 2000 or 1990 tract boundaries. Again, if you're working with historical census data and you want to get it up to 2010 boundaries, there are other tools that can help with that process. We can download these data, again, by state, in which case we need to specify which state we're looking for, and also by county if we would like. In both cases, we'll specify either the name or a FIPS code. So for the state, that would be a 2-letter abbreviation or a 2-digit number. For the county, that would be a 3-digit number or a string name, something like St. Louis City. Finally, we specify the exact variable we're looking for. So, for example, if I want to download by state, for all states, the population in 2010, I would use the getDecennial function. I'd note that the geography should be the state, the year should be 2010, and the variable should be P0010001. This would look the same if I wanted to get county, tract, or block group level data. We would just have to note the state as well for all of those sub-county level geographies. In the download data section of this lecture's notebook, the first example we have is one where we download state populations for all US states for 2010. So we specify the state for geography, 2010 for the year, and the variable number we've already discussed. When we execute that chunk, we now get a pop states object. We want to make sure we are using all of these functions and taking their output, returning that into a new object. We'll go ahead and click on pop states, and we can see that there are 52 rows, right? And there are only 52 states. And that is because the District of Columbia and Puerto Rico are returned as well with the state's geography argument. If you only want 50 states worth of data, you'll have to filter those two observations out. And that will leave you with a table that has the populations in the value column for each of those 50 states. So we'll go ahead and close that object. The next example we have here is one where we download county level population data for the state of Missouri in 2010. If we execute that chunk, we get a new object called popmo counties. We'll get some output that suggests that it has changed one of our arguments from MO for the state to 29 for the FIPS code. And so if you don't remember the FIPS codes when you're using tidycensus, that's okay. It will do its best to convert your string input into those numeric values. You can also just give the numeric value as the argument when you're using the function. We'll go ahead and open that object, and there we see each of Missouri's 115 counties and their 2010 populations in that value column. Remember that St. Louis City is its own county equivalent, has its own county level FIPS code. That makes working with city data easier than other cities in the country that are sometimes split between multiple counties or are within a county. And so, because St. Louis is a county as well as a city, we can specify St. Louis City in the county argument for the same function and get only the population for the city in 2010. So we'll go ahead and execute that code chunk. When we do, we'll get output noting that FIPS codes have been used, and we'll be able to explore an object that contains just St. Louis City's population for that year. Finally, I have some syntax for downloading 3 different populations at the tract, the block group, and the block levels. See all 3 of them here. When we execute that code, we will get 3 objects in our environment that have those corresponding data. Most data in the census are actually part of tables. So there would be, for example, a column for population count by race for white respondents, for black respondents, and then for respondents of the other census race categories. Typically, we want to download all of that at once. And so we can, instead of specifying a single variable, that would be one of those columns, we can download the entire table for race in the US Census. So we don't use the variable argument. Instead, we use a table argument, and we want to make sure we set the output to wide. There are 2 options. I'll show you what those look like in just a second. One is tidy or long format, where each census tract will appear as a row for each different measure, for white respondents, for black respondents, etc. The other is wide form, where each of those measures appears as a column. And that's typically what we want for GIS applications. I'll start by filtering the concept for the label I know exists for the race data. Now, if you weren't sure what the concept value should be, you could use some of those string tools we used last week to detect, for example, the word race in this variable. And what we see here is that there are 8 different race variables. All have the same beginning to their name, P003. That's going to be the table number. So those first 4 characters are going to be the table that we're going to search by when we download those data. And we'll download that table down here. So I'll specify the table number, I'll specify output tidy to show you what those data looks like. We'll use the glimpse function from dplyr to illustrate that we get, instead of 106 census tracts, we get 848 tracts. And that's because we are getting 1 row per variable, not 1 row per tract. Again, this is not typically what we want for GIS applications. So you can see here all of the rows for the first variable, 1 per tract. We scroll through that in our notebook. We will eventually get to the page where the second variable begins. So these are what are called long data, but we usually want wide. Down here, I will execute a similar function. All I've changed is that the output is set to wide, and then we'll go ahead and use glimpse again to preview how they've changed. So instead of having 848 rows, we now only have 106, and we have a variable for each of the race measures we are interested in observing. Finally, I want to discuss how we obtain American Community Survey data. Remember that the ACS is the tool for obtaining population estimates between census years. It has a different set of questions, and so when we use the load variables function from tidycensus and we specify an ACS year like 2016 as well as the ACS product, ACS5, those are 5-year estimates, we will get different output. Our notebook contains some sample code for getting all of those variables from the 2016 American Community Survey. We'll load it into an object called ACS. Go ahead and open that object up, and you can see there's nearly 23,000 variables, so it's very extensive. Too extensive really to scroll through, and so it's much easier to search for the things we're interested in, like perhaps household level estimates. Again, even when we use a keyword, we may see far more variables than what we can reasonably search through. So working with the ACS can be tricky until you know what variables you're looking for. One of the reasons I show you the American Fact Finder website in the first video is that American Fact Finder, while getting data out of it can be frustrating, is a great way to search through different census products to find the things we're interested in. It has some tools for narrowing down observations and variables in ways that are helpful, particularly when you're first starting out using census products. So if we have a variable we know exists, like B11001, which are the estimates for different household types per geographic unit, we can use that ACS table to search for that table and see all the different columns that are potentially available to us. So all different estimates, different combinations of family households by race, as well as non-family households. Once you have a variable name, we use the getACS function to specify the data we want to download. The parameters are going to be largely the same as those that we used for the census arguments: geography, year, state, county, etc. But we have an extra argument now, the survey parameter. So we'll use the 5-year average estimates for this course, ACS5, along with specifying the variable we're interested in. We can see an example of the getACS function in action here beginning on line 135, where we'll download a count of the number of households in each county in Missouri. We'll do that for the 2016 ACS. We'll download a single variable, 11001001, which we can see here in the ACS's table, which is the total estimate for the number of households. Execute that code block. And now we have, for each county in Missouri, an estimate of the number of households that exist in that geography. You can see there is an estimate column and a margin of error column. Because the ACS does not talk to every single person in every geography in the United States like the census does, they come with margins of error. These are 90% margins of error. What they refer to are the number of people we believe that estimate to be off by, either way. So plus or minus 100 people if that MOE value is 100. We can see similar data at the tract level for the same variable. You'll notice that the margin is not that different for specific census tracts, but the estimate's quite a bit smaller. What this means is that the tract level data is subject to a higher amount of error than the county level data. And so with the ACS, typically the smaller you go in terms of geographic unit, the higher the amount of error that's present in each of those estimates. Like the census data, tables from the ACS can also be downloaded instead of downloading single variables at a time. The options are the same. We specify a table in lieu of a variable, and we set the output to wide, just as we did with the census data. The function shown here at the bottom of the Lecture 08B notebook has that same syntax. In this case, we're downloading tract level data for the city of St. Louis. Note that the county ID is 510, that's the city's FIPS code. And we are getting a count of the total number of households plus all of the other household level data associated with that table, which will be broken down by race, different numbers of households. We've also set the output to wide. So when we execute that code, we can open up the object and we'll see each of the columns, which is a different variable or a margin of error associated with that variable for each of the measures contained in